In the harsh and dynamic environment of construction sites, heavy machinery poses significant risks to worker safety. Traditional safety protocols, relying on human vigilance, training, and manual oversight, have proven insufficient, with construction remaining one of the most hazardous industries worldwide. Statistics reveal that a substantial percentage of construction fatalities involve heavy machinery, with many incidents occurring due to proximity issues, operator inattention, or workers entering restricted zones. The heavy machinery safety algorithm represents a paradigm shift in construction safety, moving from reactive to proactive, from human-dependent to AI-enhanced, and from isolated safety measures to integrated, real-time monitoring. This sophisticated mathematical model continuously assesses risk factors, calculates safety scores, and triggers appropriate interventions before accidents occur. Core components of the algorithm. At its heart, the algorithm operates on 4 primary risk factors that comprehensive research has identified as the most critical predictors of heavy machinery accidents. Proximity risk, P. Perhaps the most immediate danger comes from workers being too close to operating machinery. The algorithm calculates this risk using the inverse relationship to distance, P equals 1, D, where D is the distance in meters between a worker and a machine. This elegant formulation ensures that risk increases exponentially as distance decreases, reflecting the real-world dynamics of construction accidents. Speed risk, S. The velocity at which machinery operates directly affects the severity and likelihood of accidents. Higher speeds reduce reaction time and increase impact force. The algorithm quantifies this through a normalized speed risk factor. Hazard risk, H. Environmental conditions, such as poor visibility, unstable terrain, or confined spaces, can significantly elevate accident risk. The algorithm incorporates site-specific hazard factors that adapt to changing conditions. Alertness risk, A. Operator fatigue or inattention plays a critical role in machinery accidents. Through operator-facing sensors that monitor eye movements, posture changes, and control inputs, the algorithm continuously assesses alertness levels. The mathematical model. These 4 risk factors combine in a weighted formula to produce a comprehensive safety score. Safety score equals 100, WP plus WS plus WH plus WA, where W, and W are carefully calibrated weights that reflect the relative importance of each risk factor based on historical accident data and site-specific conditions. The score begins at a perfect 100 and decreases as risk factors increase. The beauty of this formula lies in its adaptability and interpretability. Graduated response system. Rather than a binary safe-unsafe determination, the algorithm implements a graduated response system with distinct thresholds. Low risk, safety score greater than 80, normal operations continue with ongoing monitoring. Medium risk, 60 less than safety score is less than or equal to 80, the system issues visual and audible warnings to both workers and operators. Machine operations might automatically slow down in the affected area. High risk, safety score is less than or equal to 60, the system triggers immediate safety protocols, potentially including automatic machinery slowdown or shutdown, depending on the configuration. This nuanced approach minimizes unnecessary work disruptions while maintaining an unwavering commitment to worker safety. Real-world implementation. The algorithm is implemented through a sophisticated sensor network deployed across the construction site. Lidar sensors and computer vision. Mounted on machinery and fixed positions throughout the site, these technologies create a real-time 3D map of worker and machinery positions, accurately measuring distances even in challenging visibility conditions. Operator monitoring systems. Cabin-mounted cameras and sensors track operator alertness through eye movement, posture, and control input patterns. Environmental sensors. Weather stations, visibility meters, and terrain stability monitors feed real-time hazard data into the system. Edge computing units. Powerful on-site processors analyze sensor data with minimal latency, ensuring real-time risk assessment and response. Machinery control interfaces. Direct connections to machinery control systems allow for automated speed adjustments or emergency stops when necessary. Worker wearables. Smart helmets or vests provide immediate haptic, visual, or audible warnings to workers when risk levels increase. Case study. Excavator operations. Consider an excavator operating in a busy section of a construction site. The algorithm continuously monitors the distance between the excavator and all workers within its operational radius, the excavator's speed and movement patterns, environmental factors like visibility and ground stability, and the operator's alertness level through cabin sensors. Let's examine a specific scenario. A worker approaches within 2 meters of the excavator's counterweight while the operator is focused on a task in the opposite direction. The algorithm calculates proximity risk equals 1/2 equals 0.5, speed risk equals 0.7, excavator is in active operation, hazard risk equals 0.4, moderate visibility issues, alertness risk equals 0.2, operator attention directed elsewhere. With weights of 10 for each factor, the safety score becomes 110 times 0.5 plus 10 times 0.7 plus 10 times 0.4 plus 10 times 0.2 equals 118 equals 82. This score of 82 would trigger a first-level alert, perhaps a warning light on the worker's smart helmet and a notification on the operator's dashboard. If the worker moves closer or the operator becomes more distracted, the score would quickly drop, potentially triggering machinery slowdown or stoppage. Comparative advantages over traditional safety measures. The algorithm offers several transformative advantages over conventional safety approaches. Proactive versus reactive. Traditional safety measures often respond after a near miss or incident occurs. The algorithm predicts and prevents accidents before they happen. Continuous versus intermittent. Unlike spot safety checks or periodic inspections, the algorithm provides uninterrupted monitoring throughout the workday. Comprehensive versus fragmented. The algorithm integrates multiple risk factors simultaneously, rather than addressing individual hazards in isolation. Adaptive versus static. Safety protocols can adapt in real time to changing conditions, rather than relying on fixed procedures that may not address emerging hazards. Objective versus subjective. The algorithm provides consistent, quantitative risk assessments, reducing the variability inherent in human judgment. Beyond accident prevention. Additional benefits. While preventing accidents remains the primary goal, the system delivers additional valuable benefits, data-driven safety improvements. The continuous collection of safety data allows for trend analysis, identifying recurring hazards or operational inefficiencies. Optimized workflows. Analysis of movement patterns and proximity data can help redesign workflows for both safety and efficiency. Insurance and compliance benefits. Documented safety protocols and reduced incident rates can lead to lower insurance premiums and simplified regulatory compliance. Psychological safety. Workers report greater confidence and reduced stress when operating in environments with active safety monitoring. Implementation challenges and solutions. Despite its transformative potential, implementing the algorithm presents several challenges. Sensor reliability, dust, vibration, and weather can affect sensor performance. The system uses redundant sensors and self-diagnostic capabilities to maintain accuracy. The implementation focuses strictly on safety-critical data, avoiding unnecessary surveillance. Integration with legacy equipment. Older machinery may lack digital control interfaces. Retrofit kits with independent emergency stop systems address this limitation. Intuitive warning systems and graduated onboarding minimize this challenge. Future directions. The algorithm continues to evolve, with several promising enhancements on the horizon. Machine learning integration. Future versions will incorporate machine learning to identify site-specific risk patterns and refine risk weightings automatically. Broader risk factors. Additional inputs such as worker experience levels, equipment maintenance status, and task complexity will further enhance risk assessment. Cross-equipment coordination. The system will eventually coordinate safety measures across multiple machines working in proximity. Predictive analytics. Advanced versions will predict potential hazards based on workflow patterns before they develop into immediate risks. Conclusion. The heavy machinery safety algorithm represents a quantum leap forward in construction safety technology. By continuously monitoring multiple risk factors, calculating real-time safety scores, and implementing graduated interventions, it creates a proactive safety ecosystem that protects workers while maintaining operational efficiency. As construction sites continue to embrace digitalization, this algorithm stands as a powerful example of how mathematical modeling and sensor technology can transform one of the world's most dangerous industries into a significantly safer working environment. The result is not just fewer accidents and saved lives, but a fundamental shift in how we approach construction safety, from a necessary compliance burden to an integrated, data-driven practice that enhances both worker protection and operational excellence.